Hi everyone, I'm here today to talk to you about networking and Go, but before I jump into that, a little bit about myself. My name is Sneha Inguva. I'm a software engineer at DigitalOcean, and that is a photo of my cat, which I had to include for cat tax. So moving on, has anyone here heard of DigitalOcean? Oh, that's awesome. I guess we're doing something right. We are a cloud hosting company located all around the world. We have about 12 data centers at this point, more than 1 million droplets, or what we like to call virtual machines. And we have a host of other products. Most recently, Kubernetes as a service, which is super exciting, database as a service, different types of storage, object or block, VPC, and a bunch of other networking products. So my talk today is actually a little bit about my journey as a software engineer at DigitalOcean. So let's go back to 2016. This was the year I joined DigitalOcean, and when I joined, I had no experience with Go. My background was with writing casino games for gaming companies in C++, or doing full stack development, but Go was something that was completely new. I soon learned that Go has this adorable mascot, this gopher, but maybe more importantly, Go was designed as a systems language by a bunch of Googlers meant to increase developer productivity. If we really want to get into definitions, it is a statically typed, memory-safe, compiled programming language. A lot of people like Go because it has excellent concurrency support, and we're just going to go through a few of what that actually means. So there's these things called Go routines, and if you are familiar with Go, you've heard of it, you've probably heard of Go routines. They are lightweight processes that are multiplexed onto threads. It's very easy to start a Go routine. Essentially, you type Go in front of a function. There's also the package called sync, which is part of the standard library. It has a lot of very useful concurrency primitives. It has mutexes, something called sync maps, which are thread safe. It has a variety of different types of actor Go routine groups, whether it's error groups or wake groups. And we're actually going to get into these with some examples in a little bit, so don't worry about them. And then finally, there's channels, which are both loved and frequently hated. They're essentially a conduit through which you can send or receive data, often between different Go routines with typed operators. So despite having all of these concurrency features, I would say that Go is pretty syntactically simple. When I joined DigitalOcean, I found that I could grok a lot of our code in our mono repo that was written in Go. Furthermore, I found that even for a lot of open source Go software, it's fairly easy to read. And then I like to think, or actually my colleague pointed this out, that Go, compared to a lot of other languages, does enforce a coding style. And a lot of people don't like it, but some also like this because, especially as a newer engineer onboarding onto a code base, this can be a good thing. So that was 2016, but by 2017, I was working on internal developer tooling at DigitalOcean. So this meant I worked with Kubernetes, specifically how we could use Kubernetes internally. I also, and if you're not familiar with Kubernetes, it is a container orchestration and scheduling solution. I also worked a lot with Prometheus, which is a pull-based monitoring solution that's become very popular as well. So through these experiences, I also kind of saw the age of DigitalOcean kind of breaking down its monoliths into a bunch of microservices, meaning these small, I guess loosely coupled, very easily deployable pieces of code. So once we actually broke down the monoliths into a bunch of microservices, we started to containerize them using Docker. Once we had a ton of containers, we realized that we should, in fact, use something like Kubernetes to manage and schedule these containers, but then also get a lot of the awesome features that Kubernetes has available. But Kubernetes alone can be a little bit complicated to use, so we decided to build an internal abstraction layer on top of it, known as DOCC, or the DigitalOcean Command Center, which is very obvious naming there. But now that we had a bunch of pods running in Kubernetes, pods being like a group of containers, We also happened to have a bunch of services that were still running as hypervisor daemons. We had a ton of hypervisors in a ton of data centers. We also had a lot of virtual machines, and we had our Kubernetes clusters themselves. We realized that there were a lot of moving parts, and we definitely needed some introspection into these services, which led us to the 3 pillars of observability. Has everyone heard of the 3 pillars of observability? Okay, I'm just gonna quickly go through that definition as well. There's distributed tracing. So it's a way to construct a directed acyclic graph of, directed acyclic graph as you have these spans, which are timed operations, and certain context created and propagated through these timed operations throughout your services. Tracing also allows you to break down and look into causality of certain latency issues, so it's very useful in that sense. We also have centralized logging, so all our logs from different services in both Kubernetes or maybe running on the hypervisor themselves do get sent to a centralized logging cluster. And then finally, we also started to get metrics using that Prometheus solution, which I mentioned, essentially a time series of data from instrumented services. So I mentioned that we use Prometheus, but really, the truth is that we used a lot of Promethei. We actually had a setup that sort of functionally sharded them, and we used them to monitor everything from both the hypervisors and the virtual machines to the Kubernetes clusters themselves to different services that were running both on the hypervisors or in Kubernetes. The result was we got these beautiful dashboards of different services. We got wonderful distributed traces and could really break down the latency of our services, or maybe break down the latency of a call as it traversed all the way from like the front end to the lowest part of the hypervisor. And we could also look at our logs. That was great. But around this time, I realized that I wanted a different sort of challenge. For the last 2 years, I'd largely worked on internal developer tooling, but I kind of wanted to work closer to the cloud primitives, meaning like networking or storage or compute. And then I also wanted to work closer to building the products for our actual customers. So in 2018, last year, I ended up moving over to the networking team. One of the first things, or specifically the software-defined networking team, and one of the first things that I worked on at DigitalOcean in the networking pillar was DHCP, or our implementation of a DHCP server. And then I eventually moved on, and currently I'm working on the gateways team, which is kind of changing our networking architecture. So when I joined the networking team, there are a lot of terms that, especially coming from a background that wasn't in computer science, that I had heard thrown around, but I became very intimately familiar with. For example, the OSI model, learning about a socket, the different types of socket programming, all the ways in which one could use a socket. And then finally, I had a huge awakening and learned a lot about different network protocols and how to implement them as well. But this year, I guess at the beginning of this year, after having all this networking experience over the last year, I also realized that it might be fun to just randomly build other networking primitives. Obviously not something that was necessarily production ready, because building a production ready load balancer is a lot of work, but more so just something fun to kind of understand the concepts and the fundamentals underlying these services. So that led me to actually the subject of my talk today, which is how and when to use Go to build networking primitives. So our plan was we're first going to talk about why you might want to use Go and perhaps when not to use Go. Both important things to consider. We're then going to dive deep into the networking stack and define some of those terms that I had mentioned before. Then finally, we're going to end with actual examples and some code snippets, I promise they won't be long, of different network primitives. So for example, a layer 7 versus a layer 4 load balancer, a port scanner, or a DHCP server. So let's start. Why might you want to use Go to build networking services? There's a lot of reasons. There are those concurrency primitives that I mentioned before. We've got our Go routines, our channels, our sync package. Go is also meant to be used server-side, and for a lot of our networking services, they are in fact either powering the cloud, running in Kubernetes, running server-side, or actually running on the hypervisors themselves as daemons. Go also has a lot of third-party packages that make it particularly easy to use for building CLI tools. Furthermore, one of my colleagues pointed both of these things out. He finds that Go makes it very easy to fuzz test services, and especially when you're dealing with networking services that may get customer traffic, this is pretty important. And then finally, he also found that compared to some other languages, it was very easy to write RESTful or RPC services in Go. So when might Go not be the answer? So we clearly saw a lot of reasons why Go is awesome, but if you're doing some really high performance packet processing, and this is something that we've also very extensively discussed in our team, Go might not be the answer for you. So maybe if you need to receive 1 million packets per second, for example, then in this case, there are languages that are better suited for this. And even if you happen to write your networking service in Go, for example, if you wanted to have user space IO, you would still need to compile your program with C binding. So it might just be easier to do this in another language. But why do we use Go? We being DigitalOcean. Well, first of all, we already use Go so much. We actually have a mono repo called Cthulhu. And in fact, our mono repo actually has a logo as well, which you can see right there. We have a lot of shared packages within Cthulhu, which make it very convenient to write a service in Go within the mono repo. For example, we have a wrapper around gRPC that automatically instruments all our gRPC services to have metrics. We also have wrappers around the Prometheus Golang client. We have wrappers around tracing. We also have an internal logging library. There's a lot of things that, especially for new developers, when you write a Go service within Cthulhu, it's very easy to get it up and running and have it instrumented with everything you need for observability. On top of that, a lot of our networking services, as I mentioned, use gRPC. We also use a lot of CLI tools, both for debugging or for whatever reason. So here's kind of an example of some of the services that are running on our hypervisor. As you can see, we're making a lot of gRPC calls. We also have CLI tooling. And then finally, I think this is maybe the most important thing. There's this whole adage about engineers solving for performance before it's ever an issue. Well, in this case, we extensively load test most of our services before they ever go into production. And what we found, especially this comment has to do with something that we recently wrote for the most recent project. We found that already our service was good enough that was written in Go to even handle abusive traffic. And so we didn't really need more performance. In fact, we would actually be handling and throttling that traffic before it ever even hit our service due to the fact that it would be abusive if it ever got to that level. So that's why we use Go at DigitalOcean. But let's now dive into the networking stack. So some of these terms that I mentioned before, OSI, or Open Systems Interconnect Model. So the OSI model is a framework for thinking about how packets might traverse a communications network. So if you have studied computer science or you're interested in networking, you've probably heard of this. If, like me, you hadn't, this, in a way, was a little bit new, especially when working more deeply with it. So each layer in the OSI model is considered to be served by the layer below it and serve the layer above it. So working from the top to the bottom, we've got our application layer, our presentation, our session, transport, which is layer 4, network, data link, and all the way down to layer 1, which is our physical layer. Finally, there's also the TCP/IP model, which has become popular and is quite frequently used alongside the OSI model. So in the TCP/IP model, we actually combine the top 3 layers and the bottom 2 layers to have just the application, transport, network, and physical layers. Something I really want to hone in on, and this is actually going to be very important when we start discussing those networking primitives, is the idea of data encapsulation. Basically, what happens as you have your packets traversing through the layers and then having headers added or having headers stripped away. So the best way to look at this is by actually looking at the payloads and different units of data. So if we're moving from your right to your left, on the right-hand side, we have a segment, which is the unit that we're dealing with at the transport layer, or layer 4. So in our segment, we've got our TCP segment payload, we've got our protocol in the header, or our protocol port numbers in the header. But if we move down one more layer to layer 3, or the IP layer, we're now dealing with an IP packet. And so that entire TCP segment is shoved into the IP packet payload, and our layer 3 header has the destination and source IP address. If we move down yet another layer, which is in the red, we now have an Ethernet frame, and our entire IP packet is basically within the Ethernet frame payload, and our Ethernet frame header has our destination and source MAC address. Oh, okay, let's actually go back. So now that you know the types of data that we're dealing with and the different types of headers, how do we actually read this data in a program? And that brings me to the idea of sockets. More generally, they're defined as an internal network that you can use, or an internal endpoint, sorry, that you can use to send or receive data. There's a lot of different types of sockets, and I think the best way to kind of see what exists is by thinking about the different types of data. So let's talk about a segment on layer 4. How do we read a segment? Well, there's two ways. There's a TCP, or streaming socket, which provides a connection-oriented, very sequenced flow of data that will arrive in order. There's also UDP, which also happens to be a protocol, which provides kind of a connectionless flow of data, so your segments might actually arrive out of order. But if we wanted to drop down a little bit further, maybe we really wanted those layer 3 headers, or maybe we really just wanted Ethernet frames, layer 2, we would need to use something called raw sockets, which are sockets that don't have that protocol-specific higher layer formatting. So the thing I definitely want to mention, and this is something that I even struggled with because I found that quite often people would use the term raw socket and packet socket fairly interchangeably, but in fact there is a difference. The socket syscall is very similar for both. However, it does differ, and while a raw socket offers you access to layer 3 stuff, the packet socket is what will allow you to access those link layer or layer 2 headers. And this is going to be important later on. Just to add a little more complexity to this, there are other ways that you can send and receive link layer data. There's BPF interfaces, but then the BPF filters from your BPF interfaces also can be used with raw sockets, or raw sockets or packet sockets, or most frequently you've probably seen them used with TCP dump. And before we exit networking land, let's just talk really quickly about protocols. I'm just going to throw this chart up here and highlight a few things which are going to make sense when we go into our examples. So way at the top, we have our layer 7 or our application layer. You'll see we have DHCP, which is the service I mentioned that I first worked on when I moved to the networking team. There's, of course, HTTP, HTTPS. If we move down a little bit further into the transport layer, or layer 4, you see the TCP and UDP protocols. And if we move down further, other popular protocols that you've probably heard of, and layer 2, ARP protocol. Okay, so now that we've gone through that, it's probably a lot. This is pretty much my face, like constantly, when building networking services or debugging networking issues. Also my face frequently when dealing with this. But I am going to quote myself. Some might say it's narcissistic, but the best way to learn is simply by doing. And that's actually why I ended up building a lot of these services that I'm going to talk about. So let's get right down to it. Let's start with a load balancer. So first thing I built, and how this came about was, I think I just talked to some friends outside of work, mentioned that I joined the networking team. One of them mentioned, why don't we build a load balancer or just build random things? I thought it was a good idea, and we started pair programming every week to just try to build different networking concepts. So the first thing we built was a layer 7 load balancer. So before we get to it, what is a load balancer? This is probably something everyone has either encountered inadvertently, you might have not even known it, or perhaps you've dealt with it directly, or maybe you've used an open source load balancer like HAProxy. Essentially, it's a device that distributes traffic across a number of backends. So as a client, you might try to connect to a certain website, and the load balancer will actually direct you to one of multiple backends. So in our case, we wanted to build a layer 7 load balancer and use HTTP protocol. It's super simple. All we're doing is accepting client-side connections, reading a request, passing that request to one of the backends, and then returning our response back to the client. So a quick definition before we move on. HTTP protocol, that is a protocol that we will be using with our load balancer. It is request response based. It has a ton of different methods. It is stateless, and under the hood, it can use TCP or UDP sockets. But a lot of that is abstracted away in the library that we're using, which is the net HTTP library in Go. So step one in our load balancer is all we're doing is we're listening and we're serving on port 8080. And then we also have a handler function that will essentially be getting that request and then writing back a certain response. Within our handler function, you can see that in a very sophisticated manner, we're selecting very randomly one of the backends, copying over that request and sending it to the backend again. Finally, we're just going to get that response back from our backend and essentially copy it over and send it back to our client. So very simple little load balancer here. The thing though is maybe we don't actually want a layer 7 load balancer. On one hand, it takes a lot of system resources to process all the headers all the way up to layer 7. And secondly, we may not even care about what protocols go over our load balancer, which kind of led us to this layer 4 load balancer, or as we called it, the TCP proxy. So our layer 4 load balancer, a little different. Right now, instead of using that net HTTP package, we decided to directly use a streaming socket. On top of that, we decided to use a streaming socket with the TCP protocol. And then we kind of broke it down into two parts. And this is kind of a naive approach in a way, but for the sake of just us learning, we decided to do this. And I'll talk a little bit about what a real-life load balancer might do later. So we would accept client-side connections, and then for every client-side connection that we would get, we would open a backend connection and then use two Go routines. So here's that concurrency primitive in Go. We're using one Go routine to shuttle packets from the client to the backend, and we're using another Go routine to shuttle packets back from the backend to the client. So quick definition before we get to it. TCP, Transmission Control Protocol, is the connection-oriented protocol that we're using with the streaming socket for our TCP proxy. So one of the core elements of this is the TCP handshake that is used to establish a connection. So a client will essentially send a SYN, the server will respond, and then the client, once it gets that message, will acknowledge it. So to build our TCP proxy, we use the net library. We didn't actually use the net HTTP subpackage, but the net package itself to directly open that streaming socket. On top of that, we use this third-party library, which is actually based upon some elements of the standard library, but it differs in a way. And this library essentially allows us to concurrently start a number of Go routines simultaneously and then maybe exit them if one of them happens to exit. So step one is that we're going to open a TCP socket and then we're going to bind it locally to a certain port. We're going to wait from incoming connections from our client, and the client will come in with some sort of, with some remote address and source port that the OS selects, and our listener will accept that connection. So for each of those connections, we'll then move all the way in the bottom to the handle connection Go routine. And within that, as I mentioned, this is like the super naive part. We're actually opening a new backend connection. So now we're going to open and connect a backend TCP socket to a remote address and port. Once we do that, this is where we use those actor Go routines that I mentioned. We have two Go routines that we're starting at the same time. One is essentially copying packets from our client connection to our backend, and one is copying packets back from our backend to our client. And we are starting these simultaneously, and if one of them happens to exit, the other Go routine will be terminated as well.
Okay. Can we ask a question?
I mean, yeah, why not? Go ahead.
What's that syntax with the pairs of curly braces after? Like, what does that segmentation do?
Wait, which section?
Like line 2 and line, the next open brace, etc.
Oh, so you're essentially adding a function and the error function in the event that, so you're not starting the go routines until the end, but then you're essentially adding the function that you want to be run within the go routine, as well as the function that you want to be run in case it exits. Yeah. Yeah, and so within those go routines, actually, we're just essentially copying over bytes of data from the client to the backend or the backend to the client. So I mentioned that this was an extremely naive approach, and I'm going to now get into why. So layer 4 load balancers should be more efficient. In general, it's pretty inefficient to create a new connection. Every time you have an incoming client connection, we'll be doing a TCP handshake every single time in that case. In reality, what a lot of load balancers do is use something called NAT, or network address translation. Quite frequently, they will somehow munge incoming packets and perhaps just forward those packets straight to our backend. And one way would be to do that for an incoming SYN packet to establish a TCP connection, and the connection will be directly established with the backend. The other thing I want to mention is our load balancing algorithm was super simple here. We literally were just randomly selecting one of X number of backends. In reality, however, there's a lot of load balancing algorithms out there. There's IP hashing, there's the least connections method, there's round robin load balancing, by which traffic is just equally distributed amongst the backends. And something else to consider is client stickiness. And one of the methods I mentioned, IP hashing, could potentially help with that. So for example, if your backend happened to be caching some information about your clients, it would make sense for traffic from the same client to go to the same backend. So all of these things important to consider when actually making a real life production-ready, efficient load balancer. So now that we're still on layer 4, let's move over to the port scanner. So working on this port scanner, we were inspired by Nmap. If you're not familiar with it, it's a Linux utility that allows you to scan hosts and try to find open UDP or TCP ports. So here's kind of the result of using Nmap on one particular remote host. And we can see the ports that are open. We can also see there's a lot of closed ports. So actually, before I move on, so in our case, we wanted to limit this just for the sake of our example. It's easy to kind of test an open TCP port because we need to establish a connection with it. But for a connectionless protocol such as UDP, it would be a little bit more involved. Quite often, you would actually need a response from the server itself to indicate that the port is in fact open, and you might send like an ICMP request at it. So moving on, in this case, we actually ended up using the sync package. So before we had used run groups, which are based on the sync package, now we're using the sync package itself. So how do we build the TCP port scanner? This is actually even simpler than our TCP proxy because all we're doing is picking a range of ports. We're just trying to open and connect to one of those remote addresses, and then we're printing our results. If we have an error and we can't actually establish a connection, we're just going to assume that the port is closed. So step 1, same thing as before, actually very similar code. The only difference is now we're actually adding a timeout. So we're just trying to open and connect a TCP socket to a remote address and port, and if it's closed, we're printing that out. If it's open and we succeed, we're also printing that out, and we're making sure we close the connection. The other thing is, of course, we could do this all sequentially, but it would make more sense to do this concurrently. So we are using wait groups, a little bit different from the run groups from before, whereas those run groups would start after go routines at the same time. The wait groups will actually cause the main thread to block while our sub-go routines are executing. And something else that's kind of cool, which is a pattern that I've come to use a lot, is using a buffered channel, which you can kind of see at the top. We're making a channel with an empty struct that happens to have a size of 10. So I use this construct a lot to kind of limit the number of concurrent go routines that I can have in a service. So in this case, when we start our go routine, we're adding something to the channel so it fills up. When we're done with the go routine, we're reading from the channel so it empties out. So it's like a super useful construct. So in real life, however, Nmap will actually do both UDP and TCP scanning. It'll do host discovery, it'll do OS detection, And as you can imagine, all of this is very useful for auditing like security in a network, security of a firewall, security of a remote host. So we've gone all the way from layer 7 to layer 4, but maybe we wanted to go a little bit lower. And that actually brings me to the DHCP server. But before we go on, all of you are probably like, or maybe you aren't, but you should be skeptical because DHCP is technically a layer 7 protocol or application layer protocol. If you recall the OSI chart I had before, it was all the way at the top. So why are we doing this at this like layer 2? But before we get there, quick definition. DHCP protocol, it's probably used by a lot of your home routers to allocate IP addresses to networking interfaces. It's a protocol that kind of makes use of a client and a server. We actually ended up implementing the DHCP server as a hypervisor daemon at DigitalOcean, largely because we were releasing a new product that allowed customers to bring their own image. And in order for their droplets or virtual machines to actually get network connectivity, we needed to dynamically allocate those IP addresses. So how DHCP protocol typically works is, let's say on your VM, your DHCP client comes up, sends out a discover message, frequently multicasts it. Then the DHCP server will send back an offer, often with an IP address in the body. Then the DHCP client will get that. It'll send a DHCP request, and the DHCP server will acknowledge it. And then finally, frequently, the DHCP client will also do some sort of ART broadcast to verify that it is a valid IP address. So the reason that we actually wanted to drop all the way down to layer 2 is we wanted to do some kind of validation. So I mentioned before that we have that DHCP request that the client will be sending to the server. It will ultimately be having our source MAC address from our DHCP client, as well as the IP address that we're getting. What we wanted to do was confirm that the source MAC address that's in the body of the DHCP request happens to be the same as that source MAC address that is in the header of our Ethernet frame. This would allow us to kind of detect if certain DHCP clients were spoofing behavior and detect bad actors. So to build a DHCP server, however, now we're finally dropping down and we're using those raw sockets, or specifically packet sockets. So we used a library to open and bind a raw socket to an interface. Then we essentially read from that interface. We unmarshaled that DHCP message. And then we tried, depending on the type of DHCP message we had different handlers. We finally were to validate the DHCP message if it happened to be of the request type. Finally, we would craft a response and send that response back to our sender. So one of the packages that we used for this is something that my colleague actually previously wrote, Matt Layer, called the raw package. If we kind of dive into the raw package, we can see that on Linux systems, he's actually using packet sockets, essentially opening a socket, binding it to the interface, and then reading from the socket. On FreeBSD, however, he's using the BPF interfaces, which I had mentioned earlier. Something you'll also notice in both of these code examples is that we're using a bunch of other packages from the standard library. We're using OS, we're using syscall, and then we're also using this other package called Unix in order to open our sockets. So that I also want to highlight that quite frequently, and this is what Matt ended up doing, because the Go standard library, and especially the net package, didn't really have exactly what he needed for packet sockets. He created his own library using syscall and OS and the Unix package, which happens to also use syscall and OS under the hood. So in order to do this, all we're doing is opening and binding our raw socket to the interface. Something else I want to point out is when we're creating this socket and binding it to the interface, we are specifying the ether type in the header. So here we're saying ether type IPv4, meaning that we're expecting the IPv4 protocol type data to come over this raw socket. And so technically this code snippet was actually from our DHCP v4 server. So we were expecting IPv4 messages. Secondly, once we had that socket open, we would read incoming data into a buffer, kind of package that, pass it into a channel, have one of our workers in our channels handling that request. And here you can kind of see we're using that that same idea of a buffered channel and a limited number of workers to serve our requests. Same idea that we were using before when we created the port scanner. So finally, this is where we're doing that validation. We're actually reading our DHCP packet that's been pushed into another type of struct, but we're also comparing that to what we have in our packet, or in our frame header, that source MAC address. And if in fact they're not equal, we're just sending an invalid message back to our client. Otherwise, if it's not invalid, we'll just send back a happy response. So the main, obviously, the full production-ready DHCP server was way more code than this, but for the sake of this example, I just wanted to point out two main things. One, we're using raw sockets, and two, we decided to use raw sockets and jump down to the link layer because we wanted to do source MAC validation. So that leads me to my conclusion. So if there's anything you've learned from all of this, it's that Go can be good for building networking primitives. Is it always the language you want to use? Not necessarily, but it can be good. And then when we're discussing layers, for layer 7, we have the net HTTP package within the standard library. If we're jumping down further, we have the net package. And if we're jumping down even further, we have the raw package, but we can also use the OS package or the syscall package or use other third-party packages to give us access to that link layer data that we need. And even outside of networking, there's a lot of cool features in Go when it comes to concurrency primitives with the sync package, error groups, wait groups, like all of these ideas of actor Go routines being able to be started or terminated, as well as Go routines and channels. So thank you. And before I end, I just wanted to thank some of my colleagues. Matt Layer, who actually ended up writing the raw package that we used within DHCP, my other colleague, Nick, and then Julius, who happened to pair program with me on a lot of different networking primitives. So thanks. If you have any questions, too. Yeah, that's a good point. We did have to add root permissions or specific user groups in order to do this, but they were running as hypervisor level daemons, so we had that permission. For pretty much most of our networking services that are running on the hypervisor, we do have root permission and the right raw capabilities added to the groups. Yep.
When you started your talk, you talked about how you've been through the phase of DigitalOcean where you started monolithic and ended up microservices, containerization, Kubernetes, the DigitalOcean manager on top of that.
Mm-hmm.
I was curious, sort of, for a lot of small companies that want to get big, that's hopefully the trajectory they see. What were the pain points that were being addressed by each of those transitions? Like, when did you know it was time to switch from a monolithic architecture to microservices? And
yeah.
when did it become time to put those in containers?
So I would say that I think it had a lot to do with the growth of the company and the products that were being created, and then being able to have the right velocity to kind of diverge into separate pillars and separate teams. So we started, I think, moving over to using Kubernetes and the microservices when I joined the company. And before, I think, and this is true for a lot of companies, when they create their first product or their MVP, they might use something like Ruby or Rails or what have you to create it, just because it's really fast to work in. But then at a certain point, it becomes too big, and then there's also a ton of latency that's introduced. So I think it was the combination of latency, the combination of the size of the teams needing to work independently, and then also the combination of releasing a lot of products, and those products being able to be released separately or worked on by people with completely different skills. This actually kind of predates my time a little bit. I know before we even used Go, and there's still some parts that are written in Perl. I think the original founders of our company, at this point the company is like 7 or 8 years old. I think the original founders had written a lot of the backend in Perl. So that was the, I guess, original language of DigitalOcean, and then Rails. And then I think we ended up moving to Go just because it was a very easy language for people to adopt, especially people with a non-Go background or a non-like systems background. And I think that's part of the reason why it started to be adopted, I guess, maybe like in 2014 or so. And then I guess the one thing that people always ask about is why we ended up with a mono repo. In fact, I'm really surprised that I haven't had any mono repo questions yet. I don't know the original reasonings, and I think there's still some debates about it. So I think after a few years after starting to use Go, they decided to move all the code into the mono repo just because they created all these shared libraries. And then when they had a small team, it was far easier to implore teams to use the shared libraries so that every service would have observability rather than relying on every team to handle vendoring and handle setting up logging correctly and whatnot. Yeah, I think the main pain point, however, which has just been a pain point with Go in general, is vendoring and vendoring dependencies, and especially if different teams want different versions of things. But aside from that, the benefits are great. Oh, so we definitely do use context and cancellation. I think just with that particular case where I was using run groups, we didn't necessarily need context propagation, and then I wanted to have those two Go routines start at the exact same time. But we do use error groups a lot, and we do definitely use a lot of context cancellation, especially when we're dealing with like RPC services. Oh yeah, this was like, so to be clear, this was definitely not something to be used at scale. I think in terms of error handling when it comes to TCP load balancing at scale, honestly, I'm not 100% sure how things like HA proxy handle it, perhaps. That's a good question. Yeah. I mean, I think technically, especially given that you're running within these Go routines, I think also using, for example, like a retry block would be something that's entirely possible. And then I know that we've also used kind of like error channels before. We've also just immediately logged this, and then we could potentially, although this isn't the best strategy for a production load balancer, I was thinking more so just for some of our like hypervisor level services, we just immediately have them crash and systemd handles restarting them just because it's easier to do that rather than trying retry. But when it comes to a load balancer, that would be a terrible strategy. So don't do that. So like I mentioned, I think vendoring, that had been a pain point in the past. And I think that we sort of have a Go team at the company attempting to address it. So quite frankly, I think, for example, I think there's a Kubernetes like API library, and I think two different teams were using two different versions of it. And to vendor both of them into the mono repo created some issues because I think at this point we've been using Go so long that we've gone through like all the vendoring I guess, attempts in the community. So I think that was definitely one issue, and that also happened when we used Terraform. Like different teams were using different versions of it. So I think that was definitely one of the issues.
As your infrastructure started looking into Go modules and how, and Russ talks about vendoring dependency, blog posts, and how that might help your team solve that problem.
Yeah, we actually just, I think, maybe earlier this year, did start looking into Go modules. As to whether it's helped address some of the pain points, I think it might be a little too early to say definitively, but hopefully. Oh, and I guess one of the other things, speaking of monorepos, that I realized is at some point you can have a monorepo that's extremely large and that GitHub Enterprise has trouble supporting. Awesome. I guess that's pretty much it. Thank you, everyone.